Okay. So that was the first quiz. If you saw the problem, is the level of difficulty is pretty easy. So I think if you read through the slides, show up on time, and you should be okay. But again, if you missed it somehow, you can volunteer to present. So no need to be disappointed. As I mentioned, we don't check attendance, but I do want to get familiarized with your names. So Hyungjun and Juma, could you kind of show others what you did today with the name tags? Yes. So I would appreciate it if you do it because I want to get to know your names. Yes, thank you. And if you do me a favor, if you have a pen that's thick, it's easier for me to read. I'm getting old, so for instance, I can read Suhon, Sunguk, yeah, barely. But if you have a thicker pen, or yeah, that'll be great. Now, while you do that, I'm gonna call out the student names again, just for me to get to know you guys. So I'm gonna start with Baek Young-sung. Okay, are you trying to graduate this semester? No, okay, that's good to know. Kim Song-yeon. Okay, all right. Lee Hyun-jong. All right. Park Jong-hyun. Lee Seung-guk. Im Jin-sop. Jung Eui-jun. All right. Chun Su-bom. Asmir. Okay. Kim Chun-ha. Shin Hyung-jun. Woo Hae-in. Lee Seung-jun. Seung-jun. No Seung-jun. Lee Jong-min. Jong Su-hun. Junor. Okay. Kim Dong-min. All right. Jang Chun-ho. Okay. Ho Hyun. Jong Hyun-sop. Hye Jin-hyuk. Kim Seung-ye. Okay, I'm gonna try this. Bartholomew. How do you do it? No, I want to hear from you. Okay, do people call you by that, or do they call you short? Barde. Okay, Barde. It's easier. And you're originally from Poland?
Yes.
Nice.
You know that.
It shows that you're from Poland. Because they usually show your, yeah, for some reason they're showing your nationality here. Yeah. Okay, welcome. Kim Dong-wook. Okay. Chun Kyu-bom. Kim Si-yeon. Okay. Lee Chan. Here, and last but not least, Son Jin-soo. Okay. How are you guys doing with your team formation for projects? Are you guys all good? So, I mean, we got some contacts saying like your mates dropped the course, for instance. Again, we have a thread on Campus War. You can go try to find another teammate. If you want to go solo, that's fine. But again, it's a tough project, I think. So I do recommend, not require, recommend to find a teammate. Try to do that by tomorrow. If not, maybe on Wednesday during the lab session, we'll try to help you guys as well. So today, we have two topics. The first one's called limited direct execution. Now, last week, through pre-recorded video, one of the key things of OS is in giving process illusion, you have the CPU by yourself, right? And the way to do it is time sharing, right? Different processes, they need to share a CPU. So we need to decide who gets to use when, okay? Now, there are two issues to this. So when you're doing time sharing, you're gonna have to give control to some process, take back, and so forth. And you don't want that to be an excessive overhead process, right? You don't want your computer to slow down while trying to implement this, right? The other is also control, right? Somebody needs to have control, right? And who decides when to have control, by which mechanism to do this efficiently and effectively. So one way to do this, one naive way to do this is we let them do whatever they want. We let the process give it the CPU, you do whatever you want, right? Very, what do you call it? Very trusting way to do this, right? And if you actually look at the history of computing, networks, whatever, it's very trusting of the users, like security, right? When the people who developed the internet, they didn't really think about all the bad people who's going to be on the networks, because for them, initial idea is to get these people on the networks. That was hard in itself. You guys don't think of security. Same thing for us. Hey, all processes will be behaving well, so why don't we just give everything? So if you kind of look at this in the pseudocode, just do this. Right? OS starts a entry for a process list. Then you allocate that memory for the program. Basically, you get it from the disk. Then you load that program into the memory. Then you're going to set up stack with the argument count and argument vectors. You clear registers because you're basically resetting. Then you basically call the main, which is the entry point, to the program. So you set up everything for the program to run. You give entire control to the program, that then it runs main or whatever subfunctions it has. When it's done, it gives return. Then after all, the program's run, so the OS would free memory of that process and remove that from the process list. So if we do this, right, then the OS is really a library. Right? It's not doing much else, right? But obviously, this has a couple problems. Okay. So problem number one, what if these processes do something they're not supposed to do? Right? Like, let's say, let me give you an analogy. Let's say we have professors who teach courses. You as students want to take certain courses. What if you just schedule everything? I want to take OS Monday 9 a.m. Well, you say, oh, I want to take Tuesday 9 a.m. Well, I can't teach you all the time, right? It'll be chaos in a way, right? So they don't let you do that, right? The school administration does that, and we let you select whatever. So there's something you as student could do versus what the administrations do. Same with if you go work for a company. Anybody done internships or have industry experience? Nobody? Yeah? Yeah, so where did you work? What's a startup? Okay, was it like on-site or what you were doing? Did they let you in everywhere and have access to all the files? Definitely not, right? Yeah. Same everywhere you go, there are things we have access to and there are things we don't. In the computer sense, right? So some of the things that process should not do would be like issuing an IO request to a disk, right? What if we all go and try to access disk and we could be overwriting everything, right? So this is something OS has to do. Say solution to the OS for this problem is two different modes, user mode and a kernel mode. So most processes will be in a user mode. Okay, so applications do not have full access to hardware resources. On the other hand, kernel mode, basically this is where OS resides. It has access to the full resource of the machine. Now, are most of you guys like into computers? I'm guessing you are, but so have you heard of the term, oh, I'm a systems person versus I'm more of a theory person? Have you heard of that? No? Some people do. Anybody know what that means? I'm a systems person. What does that mean? So you're a grad student, right? Yeah, which lab are you in? So that's Professor 정명수. Is that, which professor is this? Kim Jung. So are you in a systems lab or are you in a theory lab? Do you think? Yeah, so he's on circuit, but to me, he's a systems person. He builds systems, but some people have different definition. But one professor I know says, if you're a systems person, it means you've actually written code in the kernel. And we'll get to that. So if you're, the Pintos is gonna be like that, for instance. So they separate it basically. So applications by default, the applications that we run, they're running on the user mode. However, applications sometimes need access to something they don't have access to. For instance, accessing file system, creating and destroying processes, communicating with other processes, and we'll have a whole chapter about this part much later in the course, but also allocating more memory, right? So these applications in the user mode sometimes need some access to the kernel mode. So the way to accommodate this in the OS is something called system call. So applications could make system calls so that they can do something, you know, in typical case, they're not allowed to do. So one key concept to do this is using trap. So if you had taken 209, you probably remember this part, trap in a system call. So the way you use it is very simple. It's an integer with a number, but we'll get a little bit into this later. Basically, what it does is that it raises the privilege level to the kernel mode. When this happens, it saves registers at the kernel stack, the per process kernel, like EIP, CS, flags, and so forth. Basically, this is to set up, okay, I'm going to go into the kernel mode, then I need to come back, and I need to resume. So you're basically setting up your return. It locates the destination in the kernel and jumps to that destination. Now, trap is basically an interrupt. You're causing an interrupt, but you also need to indicate what system call this is. So for instance, in the XV6, the number here n is 64. In Pintos, it'll be 30. So basically, to trap, all the instruction you need to do is int 0x64. Then, after you do what you need to do, you have to return from the trap. So you return into the calling user program and reduce the privilege level back to the user mode. So we know how to get into the kernel mode, right, using trap. But what code do we actually run, right? Because some instances to use trap would be like completion of disk IO. It could be a keyboard interrupt. We do things like Control-C, for instance, or it could be a system call, right? So when there's a trap, this needs to be handled, right? What trap is this and what needs to be done and where is that code? So that's something that's been done by the trap handler. Okay, so it's the code to run for each interrupt number, the trap number, right? And each OS would have all this number indicated. So as an application programmer, you will always have to look these up and write that code using that number. So typically in the OS, there's something called a trap table. There'll be a list of all those trap numbers, location of where the code resides. So when that trap is called, you know where to go and what to execute. Okay, so address of the trap handlers. Basically, hardware informs the location of the trap table to OS when booting. Every time your computer boots, this gets loaded up. The instruction to inform the location of the trap table is also privileged instruction, obviously. So you cannot execute this instruction in the user mode. So now we have a limited direct execution. This is not a direct execution. So at the boot time, in the kernel mode, the OS basically initialize the trap table. And the hardware remembers the address of the system call handler. And then when in a normal mode, again, at the OS, when it's running, you create entry for a process list, you allocate memory for the program, then load program to the memory, sets up the stack, fill the kernel stack, and then return from trap. So for the hardware, you restore registers from the kernel, move to the user mode, and jump to main, and then application again runs. And let's say now it needs to get into the kernel mode. So it calls, it makes a system call, and basically sends trap into the OS. And then the hardware, it saves registers to the kernel stack. So again, this is basically after you return from the trap, you're setting that up. Then you move to the kernel mode and jump to the trap handler, right? Because the user, when it makes a system call, it indicates what kind of trap. Then OS will handle trap and do the work of whichever system call was made by the application. Then you return from trap. So in between, again, hardware will restore those registers from kernel stack, move back to the user mode, and jump to the program counter after the trap. And then, yes, you're done. So again, basically, key thing, there's a user mode, kernel mode. So this is basically protection. You don't want all the processes in the user mode to mess up the operating system. So there's some kind of protection. However, to allow processes to, let's say, read or write IO, different things that needs to be done in the kernel mode, you can request it by using trap. Now, second problem, going back to the unlimited case, right? So we're talking about control, right? Now, how do we know process is done? How do we know when to take control back from the processes? If we just give them limited access, right? Full trust, you run CPU, right? So then we need to know when to take it back. Because again, we're trying to do time sharing, right? We can't let each process dominate, right? The CPU all in itself. So the key question number 2, how can the OS regain control of the CPU so that it can switch between processes? So there have been 2 approaches. And like I said, in the old days, people were trusting of each other. So the first one was a cooperative approach where you wait for system calls. The OS doesn't take control until each process actually make a system call, then you gain control. Then, people figured out not all people or processes behave well. So the second is a non-cooperative approach, just take control. Okay, so let's look at each. So the first one is a cooperative approach. So intuition here is that it's not completely, trusting each process, because the processes, sometimes they do give up control, right? this could be like I said, making system call, right? Because whenever it needs to do the system call, OS gains control anyways. So basically, it's just waiting for that, right? So there's also a system call called yield, right, which also gives up the access to the OS. Then in this, basically, then OS decides to run some other task. And like I said, application also transfer code to the OS when they do something illegal, right? This is not intentional, but let's say you divide by 0, or it tries to access inaccessible memory. This happens, right? It's a bug that OS gains control anyways. So again, this is something that waits until this kind of things happen. So believe it or not, even the early version of Mac did this. Now, let's say a process gets stuck in an infinite loop, right? Then you never gain control. The best solution for this is reboot, right? Which is our security blanket, reboot. Taking control, the way to implement this is a timer. So during the boot, OS will start a timer. And when this timer goes off, basically, OS takes control. Okay, so every few milliseconds, OS would get control and decide what to do. It might decide to let the current process keep going, or it might decide, hey, I need to switch to a different process. And this is all part of scheduling, right? Which we'll talk later. Every few milliseconds, OS decides what to do. Yes. Yeah. Mm-hmm. 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 Yeah, yeah, yeah. This is in the good old days. Yeah. This is the a programmer could do it. Yeah. So there is a system called yield. I don't know if many people would actually write that code, but there is a way to do it, for instance. Right, okay. So basically a timer interrupt gives the OS the ability to run a game on a CPU. Okay. So like I said, we have a scheduler that makes decision, right? So you can continue to run the current process or switch to a different one. And if we decide to switch, this is called a context switch. So context switch is actually a low-level piece of assembly code. It would have to save a few register value of the current process in the kernel stack. For instance, like kernel stack pointer, general purpose registers, program count. Then it will have to restore a few for the soon-to-be executing process from its kernel stack. So this soon-to-be run is currently not running. So it needs to get ready to run that one, right? So we need to save enough information of the current one, because if this hasn't been finished, we're gonna have to go back to it anyways. So you save it. Soon to be run, most likely it was saved before, so you're loading it back up. And then you switch to the kernel stack for the soon to be executing process. Mm-hmm. So are you familiar with the stack pointer? So it's basically like if you remember taking 209, right? For each program, basically it resides in some location, right? And it would have been somewhere right now, like based on where the program is, there's a bunch of different register values, right? You see, if you remember, those stack values go up and down based on what was executed, what variables were popped, and on and so forth. Basically, it's that. Yeah. No. So in the kernel, there are some things that you need to be in the kernel space versus user space. Yeah. So this is basically at the OS level, because you're switching, you're just trying to remember the values so that you can go back to it. When you're context switching back to this currently running process, you're basically trying to remember basically how to convert it back. So that level of details we'll cover much later. All right, thanks for the questions. Right, so again, looking at this table. Yes, so basically the new part here is this, right? You start a internal timer at the kernel mode. So you start timer and then interrupt CPU on X millisecond, X being whenever you decide to interrupt. Then let's say you're running process A and there's a timer interrupt. Then you save registers into kernel stack of A. Then you move to the kernel mode and jump to the trap handler. Yes, basically call switch. So basically, if you're switching from process A to B, right? You basically run this in the OS, and then you restore registers into your kernel stack B, move to user mode, jump to B, and then process B runs. So again, this is basically, again, A was running, there was a timer interrupt, the OS schedules B. So you save everything for process A, reload things for B, and then you run process B. Okay? Yes, so there's a context switch code. Again, this is in the assembly, so you can go check it out. I'm not gonna go line by line on this. So one might think about what happens if there's an interrupt while taking care of interrupt, right? So OS obviously will have to handle these kind of situations. So one would be if you're processing interrupt, you disable interrupt. And there's also some locking mechanisms to protect against concurrent processes, messing up internal data structures. So again, OS needs to be very detailed, right? It needs to cover all cases. Because the worst thing you want is a crash, right? A computer crash or auto reboot, right? So you need to be prepared for all these cases and protect the kernel. Okay, that's the first half of today's lecture. Any other questions? Okay, if not, let's go to the second half, which is scheduling. What is scheduling? Do you guys schedule things? You don't? Like you should every day, right? Don't you guys have a bunch of different homeworks and assignments? How do you decide when to do what? How do you decide it? What's your scheduling algorithm? Huh? Make priority. Okay, so what's the priority for the OS course? Okay, but how do you decide a priority? Like the course you want to do well, or is it the length of the task, or the difficulty level, or whether you do it alone versus do it with a team? I mean, what's your criteria? Okay. Then there must be other stuff than OS, right? Your personal things. Like what? Do you have a hobby? Well, what's your hobby, if you don't mind me asking? Playing basketball. Okay. then that should be a high priority, right? Because you need the schedule of other people as well. You can't just go shoot yourself, right? Yes. Okay, basketball, what other stuff? Playing with, what do you guys play? I mean, I'm just curious because I'm gonna, eating? Just eat? Keep eating, mukbang? Okay. Do you call your family once every what? Every major holidays? Or girlfriend? How much time? Is that the highest priority or unless she's here, can you maybe. Okay, very non-committal. So there's different things, right? Now let me just do one thing. You guys are always running out of time, right? Anybody like say, hey, I have more time than things to do, please? Nobody. All right. So let's first do this. So we're very deadline driven, let's be honest, right? Because one of the things we haven't mentioned, when is the deadline, right? So now first I'm going to use something called the importance, right? And this is up to you to decide what's more important to be priority, right? Now let's say this is deadline in terms of deadline soon or deadline far away. Okay, so let's say I'm gonna very simplistically categorize all the tasks into 4, right? One is not important, deadline far away. Can you guys see it from there? Sorry. Category 2 is very important, deadline very soon. 4 is deadline soon, not important. 3 is not important, deadline far away, right? Now, obviously, we should do this first, right? Right? Anybody disagree? Nobody, right? So we should do this first too. 3 should do last, if at all, right? Probably we might not even have to do this, but if we have time, we'll do this. The question lies in which one we should do first, 1 versus 4. But this is nothing to do with operating systems. This is, in my opinion, about life. 1. Just 1? 2? 2 people on 1, okay? How many in 4? Most of you. Okay. Most. The 2 of you on 1, you guys are winners. Yeah. If it's not important, why are you doing it? The key in life is to minimize whatever goes here, right? If you're working on this will soon go over here, and you're going to rush it. And you're going to regret, oh, why didn't I start sooner? Well, you didn't start sooner because you were busy doing this, not this. Your life has to be priority driven from now on, not deadline driven. Priority driven. If it's important, Pentos, we'll give you 3 weeks. Start immediately. Otherwise, it will reside somewhere here on deadline -1. You will start regretting. But in life in general, and as you age, and as you're in a different years in your school, but also in career, your priority will change. Like for me, for instance, work was very important. Now I'm trying to balance work versus family, which is very complicated. But for you, most of you, I think, family is probably low priority. It was a low priority for me when I was your age. But maybe girlfriend, boyfriend, very high priority, depending on how happy you are with that partner. But you have to balance it, right? But key thing, if you have very few here, in general, you'll be happy. Your life will be happier because you're not in a rush. You don't feel pressured. The key to do it is work on one if you have a bunch of stuff in one versus four. Obviously, you'll screw up a little bit in the four, but you already said this is not important. But then why are you doing it? One drawback of most students, especially those who grew up in a Korean culture, you're trying to be perfect. Well, I have bad news for you. You're not perfect, and you'll never be. You're using perfection basically to get in the way of making progress. You're not going to be perfect. Trust me, you're not going to be. No matter how hard you try, you're not going to be perfect. You should strive for excellence, but you should be excellent in things that are important to you. Okay? So that's the most important thing for scheduling for your life. Any question on this? I rarely use Blackboard. If I use it, it means it's important. Trust me, nobody will teach you. Okay? Now on to the operating systems. So we're going to learn something called MLFQ, which is multi-level feedback queue. So this is a schedule that learns from the past to predict the future. Obviously, we can't predict the future, but people typically say your past performance is a good indicator of future performance. Right? That's why some companies, they look at your GPA because that's one indicator of your past performance. So for this MLFQ, there are two objectives. One is the optimized turnaround time. This means is that it prioritizes shorter jobs first. If it's quick, just do it, get it out of the way. Okay, because it means, again, we're doing a time sharing system. There are multiple processes that needs access to CPU. If job is short, it will give more time for other processes to have access to CPU, right? So this MLFQ philosophy is that shorter jobs are better jobs. Also, minimize response time, however, without prior knowledge of job length. So that's where this thing comes through, right? You want to learn from the past to predict the future. So with two objectives in mind, let's look at some of the basic rules. So MLFQ has a number of distinct queues, and these queues represent priority. Okay. You want to categorize jobs into priority, and if you're in the same priority, then you're in the queue, right? Of course, first come, first serve. A job is ready to run on a single queue. So again, a job could be only on a queue. It can't be residing on multiple queues, obviously. And then if there are jobs in the same queue, then we're going to use round robin. Are you guys all familiar with round robin? Okay, all right. So rule number one, if priority A is higher than priority B, then you run A, right? So B won't run until higher priority jobs are all done. Rule number two, if you are on the same priority, then between those jobs in the same priority, we're going to run round robin. So those are the first two rules, simple enough. Now, one interesting thing about MLFQ is that it varies the priority of a job based on its observed behavior. So your priority could go higher or lower based on what you've done. Okay, so it's not a preset priority. It's not like in an airline where they put you in the economy and you stay on economy. What's economy? It means you're poor, right? It's a glorified word. You're poor, go to the back, right? It's not economy. Okay, there's first class, and then what is it? Business. What's a business? So first class, business, and poor, and we're in the poor zone, right? And they don't upgrade you. If they do, it means you actually spent a lot of money to the airline before, right? And somebody didn't show up. But in here, it can change. If you behave well during the flight, they might put you in the business class during the flight and put somebody back to the poor line. How cool would be that, right? So here, example. A job repeatedly relinquished the CPU while waiting IOs. All right, if it's doing IO, you're not running CPU, so I give you back the control. What a nice person. I'm gonna get you up maybe to even the first class. Versus a job uses CPU intensively for long periods of time. Maybe, let's say, I'm sorry to use this analogy, but I didn't prepare this. This is all coming instantaneously. Let's say there's very few bathrooms in an airline. Somebody uses for like 3 hours. You should get out of the flight, right? Reduce the priority. So based on your behavior, in terms of time sharing the CPU, your priority might get upgraded or downgraded. So the textbook uses a very simple example. High priority Q8, there's A and B, so they will use round robin. When these are done, then it goes down to Q4. And then in the end, if there are no other tasks in the higher queue, the D on the low priority would get executed. So we talk about changing priorities, but how can we do that? There needs to be some rule for this. So rule number 3, remember we already had rules number 1 and 2. So rule number 3, when a job enters the system, it is placed at the highest priority. Very generous. Everybody goes into first class. Not bad. Rule 4A. Now, if a job uses up an entire time slice while running, obviously OS will decide there's a time slice. If you're using the entire time slice, then you get demoted. Right? You're not leaving anything to share with others, then you're a bad person. Go to the back. Rule 4B, if a job gives up the CPU before the time slice is up, it stays at the same priority level. So here, for so far, you get downgraded. There's no upgrade because you start from the top. Okay? So there's a time slice. If you give up before time slice is up, it means, oh, we have remaining time to serve the other processes. So thank you very much. You stay at the top priority or whatever priority level you're in. Okay? So that's the rule. So if we do this, this is approximately shortest job first. A little different, but pretty much very similar. So with these rules, let's go through very simple examples. Now here we have time slice 10 milliseconds. One job, right? But still, a rule is a rule, right? Even if I don't know if there's going to be only one job, there might be other jobs coming up. I don't know that. So I'm just going to still execute my protocol, right? There's one job, but it's very long running, right? Now, when it enters, we have 3 queues. Q2 highest, Q0 lowest. It enters at the top. Now, after the time slice, 10 millisecond here, still running. So you get demoted to Q1. It is still running after 10 millisecond. Here it should be 20. So you get demoted to the bottom, and you just keep running it. Had some other job came in, this would have been interrupted, right? But luckily for this job, it was single, so keep going. Second example, along came a short job. So here we have 2 jobs. Job A long-running CPU-intensive job, basically the same thing as the previous slide. Job B is the second job that runs an interactive job, and let's say 20 millisecond run. Okay? So A is running. After 10 millisecond, demoted. After 10, demoted again. At T100, job B comes in, right? Remember, this runs for 20 milliseconds. So after 10, this could demote it. But note, however, while at Q0, job A was running, this new job came up, right? And this new job, when it's entering, is the highest priority. So you get interrupted, right? So here you can see this guy, job A, was suspended at 100. And now this guy, new job, gets run for 10 milliseconds. Keep running. So this get demoted. So now in Q1, still higher priority than job A. So you run for 20, about to get demoted, but this is done. So at 120, job A resumes. All right? Makes sense. Example 3, what about IO? Like IOs are pretty short, right? So again, job A, the same guy, long running, CPU intensive. Now job B here is an interactive job that needs the CPU only for 1 millisecond. Okay, so it's performing an IO. So when you're doing an IO, you don't need the CPU, but to prepare for the IO, it needs CPU for 1 millisecond. Okay, so again, this is same as before, but at 50, gets interrupted because there is a job that entered as Q2. So job A was in Q0, so it gets suspended. After 1 millisecond, this gives up. So at 51, job A resumes. But then another job comes in, high priority, uses for 1 millisecond. So this will be repeated. Right? So obviously, this algorithm prioritizes shortest job first. So this interactive IO job, very short. So this will always be in high priority. So this MLFQ works pretty okay, but it has its limitations. Okay, so the book points out 3 major issues. One is starvation. There are very large number of interactive jobs, right? Previous example, there was only one IO job coming back and forth. But what if there's many? Then long jobs, they might starve from the CPU, right? The other is gaming the scheduler, right? Misbehaving process. Let's say we know time slice is 10 milliseconds, right? After running 99%, then you choose an IU, right? Then it comes back, it will be the highest priority. It never actually reaches the time slice, but just before IO, right? So that will be unfair, right? So those cases we can't handle. Also, program might change its behavior over time, like it's a CPU bound process and now later becomes IO bound process. So how do we help these kind of processes? So it looks like we need to fine tune the algorithm a little bit. So now rule number 5. After some time period, S, you move all the jobs in the system to the topmost queue. It's sort of like a reset, giving a second chance, right? So example, a long-running job A with 2 short-running interactive jobs B and C, right? In the previous example, this guy would get stuck, and then let's say these 2 jobs B and C alternate each other, right? Then job A would starve. It would never access the CPU, right? Which would suck. But let's say we do a priority boost every 50 milliseconds. Right here, initially, job A is the only job. You get demoted after 10, demoted after 10, but at 50, you get a boost. You go back up. Same thing happens again, then you're here, right? You're running, then this guy comes in, right? Basically, even before you get demoted, you're basically round robin here. So you give up your CPU, then you get boosted up again. So you get access to the CPU. So you're giving a little bit more equal timeshare. Okay, so priority boost is something, one way to overcome such issue. Now, obviously, then how should we set, how often do we do the priority boost, right? Obviously, if you have a lot of data about how much, which process run for how long, then you want to simulate those kind of things and try to optimize the value. Now, rule number 4, this is about prevent gaming. We're actually going to rewrite rules 4A and 4B here. So what we're going to do is, once a job uses up its time allotment at a given level, regardless of how many times it has given up the CPU, its priority is reduced. Okay? So even if, let's say, through the IO, you give up the CPU, you're still going to get demoted. Right? So you can't misbehave like previously. I just used 99% of my allotment and then give up to maintain your priority. You can't do that, because if you reach that slot, you're going to get demoted. So previously, like here, right, you're still going to use it and give up and all that. But here, once you reach it, you're going to get demoted anyways. Okay, so this is a mechanism to prevent gaming. Okay. There are other things we can do to make this a little bit better. For instance, we can use different duration of time slices based on the queue. Let's say highest priority queue, you use shorter time slice versus lowest priority, longer time slices, right? There could be multiple directions, but I'm just showing you the one possible way. Now, MLFQ, the basis has been used in many operating systems, and we have 2 examples here. One is a Solaris. This used to be a Unix workstation developed by Sun. You probably, anybody heard of the company called Sun? Oh, you have? Wow, how did you know? Okay, anybody know Java, the programming language? Java? Do you know which company made Java? No, it was Sun. But Sun used to be, so before Microsoft, you guys know Microsoft, right? Before Microsoft, it was Sun. So if you were CS major, like in 1990s, before you were born, I guess, Sun was a place to be. They dominate the workstation. So before the PCs were booming, yeah, anyways, yeah, still times. Basically, they used time sharing scheduling class, and they had 60 different queues. They had a slowly increasing time slice length. For instance, highest priority would be 20 millisecond versus the lowest would be a few hundred milliseconds. And they had priority boosts about every 1 second. So very similar, and this is some of the parameters they used. Now, FreeBSD, on the other hand, it was MLFQ, but instead of using a queue, it actually used some formula. So you compute the priority of a process based on how much CPU a process has used. Then you boost priority by decay and take the advice from the user, like nice. So there's a command called nice. And everybody used it. So if you're running something, right? It's a very long job. You can actually do a nice in your process ID. It means, hey, give priority to others. Like, I don't need immediate thing. Whenever, if everybody's busy, give me a low priority. So that's why it's called nice, right? It's very nice. So if you do nice, right? Then, low priority. So basically taking the feedback from the user. Yeah, so if formula gets too complicated, then if you want more efficiency, you can actually use the queue. But anyway, these are just the instances to show you how MLFQ had been used in real operating systems. So to summarize, these are the 5 rules we went through. The beauty of this is it doesn't require prior knowledge on the CPU usage of a process, right? Which was the quiz question of the day, right? So without prior knowledge of how long this is going to be, you can still schedule it, rather efficiently and fairly. Yes, that should do it for today. Any questions? Hmm? So basically, the longer you're in, you get. Yeah, basically, so decay means like you're basically running, you're getting very little access. So you look at the history, right? If you're not getting anything, then you get the percent. Right. So there's a Wednesday today, TAs. There's a Wednesday class this week, right? Yes. So yeah, see you on Wednesday. Again, any questions? It's okay. You can leave. You can always access campus wire. And yes.